Okay, so now that we have studied some calculus over 2D, we sort of get the sense that understanding vector fields in R2 or subsets of R2 will give us some interesting topological information, or in particular the number of poles that that subset has. So now we're going to look at R3 and look at how to relate the different differential operators in R3 and see that if we ask the same sort of questions, then we'll get the same or similar answers about how we can relate functions and vector fields over R3 to interesting topological data about the subsets of R3 which we're working in. So let's see how that works. So we're working in R3 now, and we're going to have three differential operators. The first one is the gradient, and this one goes from C infinity functions to vector fields, and it's defined in the usual way, where the gradient of a function f is the vector field fx, fy, fz. The second one is the curl, and this one goes from vector fields to vector fields again, and it's defined as this cross product thing, where if you take the vector field f, g, h, and you take the curl of that, then that's given by the cross product I, j, k, and then these partial derivatives, and then the components of your vector field. And we have the third one, which is the divergence, and this goes from vector fields back to C infinity functions, and this is defined as a divergence of the vector field f, g, h is this expression, which is the sum of the corresponding derivatives of the components of your vector field. So when I was first learning multivariable calculus, I sort of like to keep track of these guys in terms of this sequence, which goes from C infinity functions to vector fields to C infinity functions. And this first arrow represents the gradient, and then the curl, and then the divergence. And the nice thing about the sequence is that if you take any two of these consecutive functions, then they're going to evaluate to 0. So we have that the curl of the gradient of any function f is equal to 0, and the divergence of the curl of any vector field f is equal to 0. So the reason that both of these are true, the first one is very similar to 2D, where you're going to have some derivatives of f with respect to x and y, and with respect to y and x, and they're going to have opposite signs because of this cross product, but numerically they're going to evaluate to the same thing, so those terms are going to cancel and you're going to get 0 everywhere. And this is 0 as a vector field, so it's the vector field which takes a 0 vector everywhere. And this one is equal to 0 for much the same reason, where you're going to have some derivatives of your components with respect to x and y, but they're going to have opposite signs because of the cross product again. And because they take the same value numerically, they're going to cancel out and you're going to get 0. So we'll see later that this sequence going from C infinity functions and relating them to vector fields with these differential operators is going to be one of the central tools which we'll need to describe what Rham cohomology actually is. But we can rephrase these two statements in terms of something similar to what we had in the last videos, which was that if some vector field is the gradient of a function, then that implies that the curl of your vector field is always going to be equal to 0 everywhere. And similarly, if some vector field, I guess g, is the curl of some vector field f, then this implies that the divergence of g is equal to 0 everywhere. So what we have here is that the curl equaling 0 is a necessary condition for a vector field to be the gradient of another function, and the divergence being 0 is a necessary condition for a vector field to be the curl of another vector field. Now we can ask the reverse questions, as we did before, where if the curl is equal to 0, is that sufficient to show that f is the gradient of a function? And if the divergence is 0, is that sufficient to show that g is the curl of another function, or of another vector field? And so what we'll see is that the negative answers to these questions, or in other words functions or vector fields which have 0 curl or aren't the gradient, or 0 divergence but aren't to the curl, are going to give us some interesting topological information about the domains on which they are defined. So let's start off with our question of if the curl of some vector field f is equal to 0, does this imply that f is the gradient of some function f? And so the answer is usually yes. And we can do it in much the same way that we did last time, where we can define f as being the integral over gamma of f dot dr, where the only difference here is that gamma is some path in three-dimensional space. So we start at some initial point, a, b, c, and we end up at some endpoint x, y, z, and our path is just some three-dimensional path here, gamma. Now, as before, we want to make sure that this is well defined. So we want to know that if we choose another path, gamma prime, then these two are going to give the same answers. And so maybe this is our path, gamma prime, and we can look at this line integral with respect to both of these. And to show that these two give the same answers, it's again enough to show that their difference, which is the integral over some closed loop c of f dot dr, where the closed loop is given by going along gamma in the forward direction and then going around gamma prime in the reverse direction, is this closed loop c. Now to do this, we can use the three-dimensional analog to Green's theorem, which is Stokes' theorem, and this says that this is equal to the integral over a of curl of f dot dA. So the curl of f is going to be some vector field. This region A is going to be the interior of your curve C. And so this is just going to be any two-dimensional surface in R3, so that the boundary of your two-dimensional surface is your curve C. So it can look like this. It could also look like some sort of a bubble that goes above it. And it can be any surface whatsoever that's just bounded by C. And the curl of f in this case is a vector, so we're going to need to take a dot product with dA. dA is also a vector, and what it is it's the positively oriented normal vector, which means that it satisfies the right-hand rule. I guess in this case I need to switch the orientation of C so that if you traverse C in the positive direction, which is counterclockwise, then your dA vector would need to point upwards. So if the curl of f is the zero vector field everywhere, then this is going to be equal to the integral over a of 0 dot dA, which is equal to 0. Which shows that the integral over any closed loop C is equal to 0, so which means that the integral over any two curves is the same, and which means that f is well defined. I guess f is not equal to this difference anymore, but f is equal to this part, which is equal to the same thing as this integral over any other loop. Okay, so again we have that if the curl is equal to 0 everywhere, then we expect that that vector field is the gradient of some other function. But we can find a counterexample again and see that that gives us some interesting information. So our counterexample, we don't really have to look far. Last time we found a counterexample which looked like the following: negative y over x squared plus y squared, and x over x squared plus y squared. So in order to extend this to a 3D example, all we have to do is give the third coordinate a value of 0. So geometrically, this will sort of look like a counterclockwise spiral. So you have your 3 space, and you'll have some spiral that's going counterclockwise this way. And it'll sort of be the same thing as you move up vertically. And the arrows will only point in the horizontal sort of xy plane directions. So the curl of, if we call this vector field f, the curl of f is going to be equal to 0 because the curl in the z direction is going to be just the curl of the two-dimensional part of these first two, which we verified was 0 from earlier. And the components of the curl in the x and y direction will have some sort of component of the value of the z component and the derivatives with respect to z. But because there's no dependence on z and the last component is 0, those both is going to be equal to 0. And we're going to have that the curl is going to be 0 all throughout. You can check that if you aren't convinced. But we're going to have that f is not equal to the gradient of any function f. So why is this true? Well, roughly, intuitively, you can see this because this vector field is going to look the same if you translate vertically. And so what that means is that if f were the gradient of some vector field of some function f, then this function f shouldn't have any z dependence, similarly to how this vector field f doesn't have any z dependence. Because if you were to move the input up or down, then that shouldn't change the output here because you have some sort of symmetry with respect to z on this vector field f. So there is a sort of way to formalize that and show that indeed, since this is like independent of z, then f would have to be a function of x and y. But there's a more direct way to show it, which is similar to what we did last time. And what we can do is we can take this loop in the xy plane, which is the unit circle, and look at the integral over this unit circle of f dot dr. Now, because this unit circle is in the xy plane, we're going to have that basically we can ignore the z component, and this just reduces to our integral of this vector field over the unit circle that we had last time, and that's equal to 2 pi. So again, this shows that we have some integral over a closed loop, which is non-zero, which means that we can't have a well-defined primitive function for which f is the gradient of that function, and hence f is not the gradient of any function. So where does our proof break down this time? Remember how I said that Stokes' theorem says that the integral over any curve C of f dot dr is equal to the integral over some region A of the curl of f dot dA. Now the region A could be any surface which has a boundary of C. So if our boundary is again the unit circle down here, then our region A could just be like the unit disk here. But our vector field is not defined at the origin, so that doesn't work. Perhaps we can choose some sort of a bubble which goes up here and has the unit circle as a boundary. So for example, the upper hemisphere of the unit sphere. However, that region also doesn't work because it'll have to pass through the z-axis at some point. And this vector field, not only is it not defined at the origin, but it's actually not defined on the z-axis. And the z-axis is the only points where it's not defined, because the z-axis is precisely the points where x and y are both 0. And if x and y are both 0, then that's equivalent to x squared plus y squared being 0. So what we have here is that f is a vector field from R3. What is that? R3 minus the z-axis to R3. So you choose some point on R3 minus the z-axis and map it into R3. And then this vector field has 0 curl but is not the gradient of some function. And the fact that such a vector field exists sort of indicates the fact that we're missing this one-dimensional hole in our three-dimensional space. So in 2 dimensions, we sort of had that this function had to have some singular point hole so that we could not contract our loop to 0, or we could not conclude that the integral over some closed loop is equal to 0. But in this case, if we have any surface over which this vector field is defined and has the boundary of this closed loop, then by Stokes' theorem, that line integral must be equal to 0. So in order to not be able to find some surface A, you have to have some sort of a one-dimensional hole, like this vertical line, so that if you were to have some surface which has this loop as its boundary, then that surface would have to intersect this vertical line at least once. And because this vector field is not defined on this vertical line, we cannot use this to conclude that this line integral is equal to 0. So what we see is, like earlier, a function which, or a vector field which had 0 curl but was not the gradient, sort of represented a 0-dimensional hole or a singular point hole. But in this case, what we have is a vector field which has 0 curl but is not the gradient represents a 1-dimensional hole, which in this case is the z-axis. And that turns out to be true in general, as we'll see in later videos. Now we can ask our second question, which has to do with this part of our sequence. So the first part of our sequence related the gradient and the curl. So the second part of the sequence relates the divergence and the curl. So the question is, if the divergence of some vector field G is equal to 0, is G equal to the curl of some other vector field F? And the answer to this question is, again, usually yes, but not always, depending on the topology of your space. So this is a bit less clear about why the answer is usually yes, because we don't have an easy way of constructing an inverse curl function. So if we have some vector field G, then if the curl was equal to 0, then we could easily figure out what an anti-gradient would be by integrating our vector field over a curve and using the fundamental theorem of calculus. However, in this case, we can't do that, and the inverse curl is a bit more difficult to get your hands on. However, just take my word for it that if you're working with a vector field that's defined on all of R3, and the divergence equal to 0, then that does usually imply that g is the curl of a function. So what that means is that if you have a vector field g, which has 0 divergence everywhere, but it's not the curl of a function, then that must mean that there is some hole in your space. So the example that you have here is, or the counterexample, I guess, is this vector field x over x squared plus y squared plus z squared to the power of 3/2 y over x squared plus y squared plus z squared to the power of 3/2 and z over x squared plus y squared plus z squared to the power of 3/2. Okay, so let's first show that the divergence of this guy is equal to 0. So let's look at what the derivative of this with respect to x is. So that'll be using the quotient rule, x squared plus y squared plus z squared to the power of 3/2 minus x times 3/2 times 2x times x squared plus y squared plus z squared to the power of 1/2. So that's just using the power rule and the chain rule on this part and simplifying that. And this is going to be divided by x squared plus y squared plus z squared cubed. So we can simplify this a bit, and we can see that this part, the 2's cancel, and the x's we combine into x squared. So we're going to get something that looks like 3x squared times this expression. So that's the derivative. This is the derivative of the first part with respect to x. And if we look at the derivative of this part with respect to y and this part with respect to z, we're going to see that we have some very similar expressions. We're going to get this factor from each of them. So if we sum the three things together, we're going to get 3 of these. And we're going to have to subtract off something that looks like this, except we're going to have a minus 3 squared for this part and a 3z squared for this part. And so what happens here is this becomes 3 times x squared plus y squared plus z squared, and then times this expression means that we can replace this with 3 times x squared plus y squared plus z squared to the power of 3/2. And what that does is it cancels out this term and this term, and then we get that the divergence of g, which is equal to this, is going to be equal to 0 everywhere. However, I claim that this vector field cannot be the curl of any vector field, and hopefully in anticipation of what we've done earlier, you should begin to suspect that this vector field is not defined when x, y, and z are all equal to 0, so it must have something to do with the fact that g is not defined at the origin. So again, because we don't have an explicit formula for an inverse curl, it's a bit more difficult to show that g is not the inverse curl, g is not the curl of some vector field. But we can use a clever trick, which is we're gonna first start off with sort of the analog of Stokes' theorems or Green's theorem, which relates to divergence, which is given a good name. It's called the divergence theorem. And it says that given some vector field g, if we have some surface S, which looks like this, which bounds some volume V, then the double integral of g dot dn over S is equal to the triple integral over V of the divergence of g dEV. So here, dn is going to be the unit outward facing normal, and the divergence of g is going to be some function, and so it makes sense to integrate some function with respect to a volume. And here, since you have a vector field, it makes sense to take the dot product with some like differential vector field and take that integral. So the sort of intuitive explanation for this is this side measures the total amount of some material which is exiting your surface, and this side measures the amount of material that's being created or absorbed inside your volume interior. And so this part sort of looks like something we had earlier, where you're taking the integral of something where the divergence on the inside is equal to 0 by assumption everywhere. So this side should be equal to 0, except it's not defined at the origin. So maybe we should take some surface which surrounds the origin, and show that this integral is non-zero, and use that somehow to arrive at a contradiction. Because remember earlier we used Stokes' theorem to show that something analogous to this side was non-zero, and we used that to show that we have some well-definedness issues for our potential function. So in this case, what we'll do is we'll simply take our surface S to be the unit sphere S2 in three-dimensional space. And so we can directly evaluate the double integral over S2 of g dot dn. So you might recognize that g is just equal to this vector field r over magnitude of r cubed, where r is your vector field x, y, z, and norm of r is just the dot product of r with itself, and then square root of that. So we can use that over here, and we can notice that dn in this case is just going to be r hat times r squared cosine theta d theta d phi, just because we're looking at the normal vector to a surface of the unit sphere. And so what we get here is the double integral of r dot r hat, and because the radius is equal to 1, both of these will just cancel out and evaluate to 1, divided by magnitude of r cubed. Again, this is just equal to 1 times cosine theta r squared cosine theta d phi. And again, r is equal to 1 in this case because we're looking at the unit sphere, and so this will also become 1. So what we're looking at here is the double integral of cosine theta d phi. And theta is going to vary from 0 to pi, and phi is going to vary from 0 to 2 pi. And so you can split this integral in terms of theta and phi independently and show that this is going to be equal to 4 pi. So what we have here is that we expect that this is equal to 0, right? Because the divergence of v is equal to 0 everywhere inside this volume, except at the origin. And what we find here is that this left-hand side is equal to 4 pi. So this doesn't immediately show us that G cannot be the curl of some vector field F, because we don't have something that looks like a curl of a vector field in this expression. But we can use the fact that this double integral over S is equal to 4 pi to show that we cannot have such an expression. So to do that, let's assume that G is equal to the curl of some vector field F. And let's do the following. Let's look at this contour, which is the unit circle in the xy plane, and let's call that curve C. And let's try and analyze what the integral of C of f dot dr is going to be equal to. So what we can do is we can split this up and evaluate it in two different ways. So what we have is, by Stokes' theorem, this is going to be the double integral over what I'll call A1. And A1 is going to be this top hemisphere of curl of f dot dA. And dA in this case is going to be this outward facing normal, because if C goes counterclockwise, then the outward facing normal is going to be positively oriented. But it's also equal to the double integral over A2 of curl of f dot dA, again by Stokes' theorem, where A2 is going to be the lower hemisphere. In this case, dA is going to be the inward facing normal. And if C is oriented counterclockwise, then the inward facing normal of the unit sphere is going to be the positively oriented normal that we need. And so you can see that that should be the correct orientations for the normal vectors, because if you were to sort of push this upper hemisphere down into the lower hemisphere, then the arrows would point in the same direction. So we want to use this fact to get a contradiction over here and show that since the integral over the unit sphere is 4 pi and not 0, these two integrals cannot possibly be the same thing. So similarly to what we had before, let's try and take the difference of these two. So the difference of these two is going to be the integral, it turns out, over S2 of the curl of f dot dA. And why is this true? Well, if you were to subtract off this integral, then what you can do is you can add this integral, but change the orientation of your unit normal vector, minus dA. And so what that does is, if you have your unit sphere over here, then the minus dA would be this outward facing normal down here, because the positively oriented normal was facing inwards initially. And this positive dA up here would be this outward facing normal up here. So if you were to add both of these quantities, then all you're doing is you're integrating over the unit sphere of curl of f. But curl of f, by assumption, is equal to g. So this is the double integral over S2 of g dot dA. And we concluded this was 4 pi. So what we see is that these two values, the difference between the integral over this upper hemisphere and the integral over this lower hemisphere, is equal to 4 pi and not 0. And so what that means is that we have an issue of well-definedness, not of like the value of our vector field f, but of the value of the integral over S1, where S1 is this unit circle in the xy plane of f dot dr. So again, we see that this sort of fact that this cannot be well defined is a contradiction to the assumption that G is the curl of some vector field f. And so what that means is that G is some vector field which has zero divergence. So it matches 0 over here, but it does not come from anything over here. And so if something is defined on all of R3 and it has zero divergence, then it is going to be the curl of some vector field. But over here we have a counterexample, and that corresponds to the fact that G is a vector field from R3 minus the origin to R3. So you take some point on R3 minus the origin, and the vector field is only defined on those points. So here we see that at this step, if you have something which has zero curl, but it's not the gradient of something, then that represents sort of one-dimensional holes, like we saw with the z-axis. But if you have something which has zero divergence, but isn't the curl of something, then that represents a zero-dimensional hole, like the origin over here, where G is not defined. So again, we see something sort of interesting, where these questions of whether being 0 for one differential operator means that you can be expressed as the differential operator of some other object, a negative answer to that yields some information about like the topological holes that your space has. And we see that like these sort of give different informations based on which differential operators you're looking at. So let's remark on some interesting things about these. First off, we saw that like something crucial that we've kept on using is these sort of like formulas which relate one integral to another integral, either Green's theorem or Stokes' theorem or the divergence theorem. And so these they come together to become something general called the generalized Stokes theorem, and that is very important in sort of relating the Rham cohomology to topology. And another thing to notice is that here, in our vector fields case where we had something of zero curl but it's not the gradient of something, then similarly to our arguing from our previous videos, if we were to subtract off some multiple of this vector field from some other function which has zero curl but is not the gradient of something, then we should expect that that difference should be able to give us the gradient of some function. So what I mean by that is like if G is some vector field on R3 minus the z-axis to R3, then if we take G minus some sufficient lambda f, where f is our vector field from earlier, then this should be expressible as the gradient of some function G. And we can do this because we can use a similar argument as before, where we have an explicit construction of an inverse gradient. But it's less clear that this vector field G is our only obstruction on R3 minus 0 of producing an inverse curl. So it's not completely clear that if the divergence of H is equal to 0, and H is defined on R3 minus 0 to R3, then is it true that H is equal to some lambda times G plus the curl of some other vector field j. So it's not completely clear that this should be the case. It turns out that that's true, but since we don't have a method of computing the inverse curl directly, we can't quite see that immediately. But anyways, hopefully this gives some ideas, more ideas, and of why these differential operators relate to each other should give topological information. And we'll sort of combine all of these together in the next video and sort of formulate what Rham cohomology actually should be.